What is the second law's role in irreversible thermodynamics? Have you ever wondered why some processes in nature seem to happen on their own while others requiring effort? This curiosity leads us to the fascinating world of thermodynamics, particularly the second law. So, what exactly is the second law's role in irreversible thermodynamics? The second law of thermodynamics is all about entropy, which is a measure of disorder in a system. It tells us that in any natural process, the total entropy of a system and its surroundings tends to increase. This means that irreversible processes are those where entropy grows, showing a loss of energy that can be used for work and a movement toward equilibrium. Let's break this down. Entropy is like a gauge of how much energy in a system is unavailable for doing work. According to the second law, in any real process that occurs, the total entropy must either increase or, in some ideal cases, stay the same. It never decreases. For example, heat naturally flows from hot objects to cold ones. This spontaneous transfer increases entropy, making it a one-way street. Now, let's talk about irreversible processes. These are situations where the system isn't in equilibrium at every moment and can't return to its starting point without changing the surroundings. Think about heat transfer between two objects at different temperatures or mixing different gases. In these cases, entropy increases, which reflects the irreversibility of the process. The second law also helps us understand the relationship between irreversibility and equilibrium. It tells us that natural processes move systems from states of non-equilibrium toward equilibrium. At equilibrium, entropy is maximized, and no further spontaneous changes can happen. Once a system reaches this point, it cannot spontaneously revert to its previous non-equilibrium state without some external work. On a more technical note, for reversible processes, entropy remains constant, meaning no net entropy is generated inside the system. However, for irreversible processes, there is a positive generation of internal entropy, indicating that the process is irreversible. This distinction is essential for scientists and engineers as it helps quantify losses and inefficiencies in real systems. Understanding the second law in the context of irreversible thermodynamics is vital in many fields, including engineering and environmental science. It guides the design of engines, refrigerators, and power plants by showing the limits of efficiency and the inevitable losses that come from irreversibility. It also explains natural occurrences like how fluids mix or how hot objects cool down. In essence, the second law of thermodynamics defines the direction of natural processes through the increase of entropy. It explains why some processes cannot be reversed without external influence and provides a framework for analyzing real-world systems that are always moving toward equilibrium with increasing entropy. This connection to everyday experiences, like heat flow and energy loss, makes these principles accessible and relevant to all of us.